All right, folks, let's take a look at dissociation of acids and bases. We remember from previous units that when we have a substance that undergoes dissociation, that substance is going to break apart, okay? It's going to dissociate or break apart into individual ions. And so we can relate this to acids and bases as well, okay? We also remember from our solutions unit that when we have a strong acid or a strong base, those are going to dissociate completely or 100%, okay? And a weak acid or a weak base is only going to partially ionize, meaning a lot of it's going to stay together, some of it will dissociate into its separate pieces. So how do we know what's a strong acid and a strong base? Of course, we remember that we've already memorized our strong acids, which is HCl, HBr, HI, HNO3, H2SO4, HClO3, and HClO4. Those are our 7 strong acids. Our strong bases, remember, was lithium down and around to calcium hydroxide, okay? And so when we look back at our periodic table here, that was lithium down and around to calcium hydroxide. Okay, those are our strong bases. Remember, strong acids and bases are both good conductors of electricity, making them strong electrolytes. And weak acids and weak bases are also electrolytes, but they are poor electrolytes because they are poor, or weak electrolytes because they are poor conductors of electricity. I want to take a few moments to look at what we call dissociation equations, and we've seen some types of dissociation equations already. In the last unit, this one's going to focus mainly on acids and bases, though. Okay, so let's look at chloric acid, HClO3. HClO3, when it dissociates, first off, we know that chloric acid is a strong acid, so it's going to get a single arrow, and this is going to dissociate into H plus ions and chlorate ions. Easy enough, okay? No big deal there. Let's go ahead and look at permanganic acid as well, which is HMNO4. Same sort of deal. The only difference here is that since HMNO4 is a weak acid, it's going to get a double arrow. Okay, and so it's going to once again dissociate into H plus and MnO4 minus ions. Notice the only difference we have here is that HMNO4 gets a double arrow because it is a weak acid. Let's take a look at barium hydroxide. It's a base. Not a lot of differences here. You're going to dissociate this one just like you would an ionic compound. So I've got BaOH2. Since it's a strong base, it gets a single arrow, and it's going to dissociate into barium ions and hydroxide ions. But check this out. I've got a 2 down here, which tells me that this is going to dissociate into 2 hydroxide ions. And so there's my dissociation equation for that. The next one that we have is a little different. The next one is a weak base, okay? And a weak base is going to still dissociate, but we have to add something special. Okay, remember, according to Arrhenius, a base is a substance which forms hydroxide ions in water. So let's look at aniline here. C6H5NH2. We have to find some way to dissociate this to where it forms a hydroxide ion in water. Well, obviously there's no oxygen here, so there's no way that I can dissociate it. Now, what I have to do with every single weak base is I have to make sure that water is included, okay? And I'm going to show water as HOH. What's going to happen is the aniline is going to reach over here, and it's going to steal a hydrogen away from water. So what's that going to give us? It's going to give us a new product and a hydroxide ion, okay? It's a weak base, so we are going to put a double arrow, and my aniline product is going to be C6H5NH3 plus, and we'll make Arrhenius happy. Here is our hydroxide ion. So all of the other, the acids and the strong bases, you can dissociate those just as you've been dissociating them in previous units, okay? The only difference is when you dissociate a weak base, you have to add water.